All right. Well, hey, everybody. Welcome back. Happy Monday. It's great to see you all. We are talking about some exciting stuff today. As you saw in the videos, we are talking about two of our more powerful tests for series convergence. And this is the ratio and root test for convergence. And I've gone ahead and thrown them up here on the screen now. Hopefully you all can see that. If you can't, just let me know. It will mean that something's gone wrong on my end, but we have these two theorems, I could call them, or these two tests to see whether a series converges or diverges. So the setup in both of them is the same. We have just any arbitrary series, a sub n, a sub n, and specifically it's a sum starting at some value, like as n goes from something up to infinity. Sum of the form a sub n. So our individual terms of the series are these a sub n's. They have some starting point. It could be n equals 0, it could be n equals 1, it could be n equals 2, it could be n equals 50, right? It doesn't really matter. And then it just goes on towards infinity. And both of these tests, as we saw, involve looking at limits of expressions involving these individual terms a sub n. Now, we've seen in the past that in order for a series to converge, the a sub n's actually have to go to 0, right? The a sub n's have to get smaller and smaller and smaller. Otherwise, you'll just be adding up, like sort of non-trivial, non-zero terms, and your series would diverge. So we already knew sort of a basic expression, which was that if the limit of the a sub n's as n goes to infinity, if that did not equal 0, then the series diverges, right? And this was our good friend, the test for divergence, right? This is what we called the test for divergence. So we've already seen an example in the past where we can determine something about convergence or divergence just by looking at a limit of these terms. So the ratio and root tests are a little more advanced than that. They involve not just looking at the limit of individual terms, but looking at some interesting expression involving those individual terms. And so in short, the ratio test involves looking at the ratio of successive terms, right? So we took the a sub n plus 1th term and divided it by the a sub nth term, right? So this is the term that is one further out in the sequence than the term in the denominator. So we took those expressions, we took the limit as n goes to infinity, and if that was equal to a value less than 1, then our original series converged. It actually converged absolutely, which meant that, not only did it converge, but if we threw absolute value signs on all of the terms, it would still converge. So very, very powerful version of convergence, stronger than conditional convergence. So if that ratio was less than 1, our series would converge absolutely. If that ratio was bigger than 1, our series would diverge. If that ratio was actually equal to 1, the ratio test is inconclusive. So we'll look at some examples of all of these going forward in a little bit, but this was the ratio test. It involved these ratios of successive terms. Now the root test is very similar, right? We still have to take a limit. We still have to see if that limit is less than 1, bigger than 1, or equal to 1. The main difference is in what we're taking the limit of. Instead of taking a ratio of terms, as in the ratio test, we are taking a root of terms, specifically the nth root of a sub n. And you know what? I did this in the video, and I just copy and pasted the same code over, so the same mistake is here. There should really be absolute value signs around each of these a sub n's. So I apologize about that. So the root test specifically involved taking the nth root of the absolute value of a sub n. And if that absolute value, or if that nth root of the absolute value of a sub n ended up converging to a limit L, and that L was less than 1, the series converged absolutely, greater than 1, the series diverges, and equal to 1, the root test is inconclusive. So I love talking about both of these tests in the same breadth because the conclusions that we're drawing are very similar, right? In fact, the conclusions are identical. They depend on what this limit is and if the limit is less than or greater than 1 or equal to 1. And so it's really fun to look at these together. The main difference is in what we're actually taking the limit of, but that's sort of encoded in the name, right? The ratio test, we're taking a limit of these ratios, and the root test, we're taking a limit of these roots. So that being said, most of today's class is really just going to be practicing some examples to get a handle on these and to gain familiarity with them. So right off the bat, before we turn to example 1, let me ask, are there any questions out there, either from the videos or from what we've said here or more broadly? Anything, any questions before we get things underway?
Can we go through like the ideal time to use either of those? Because I did.
Yeah, thanks, Deanna. That's a fantastic question. The question, as I heard it, was, can we talk through some ideal times to use these? Yes, absolutely, absolutely. In fact, one thing that I would like to do, not in this class, but maybe sort of after this class, in between this class and the next class, or in the next class, is to maybe develop some sort of overall framework or flow chart for when do we use all of these, because we're starting to accrue a lot of different tests, and it can be a little overwhelming if you look at a random series and you don't know what test to use. So big picture, you know, beyond this class, let's try to come up with a flow chart or some other line of reasoning for when to use which tests. But in this class, we'll absolutely talk about when do we want to use the ratio test, when do we want to use the root test, and those will become bullet points in our overall flow chart. Or I guess if it's a flow chart, they'll become little bubbles or something in our overall flow chart. But yeah, we'll totally talk about that. All right, let's jump ahead. So I want to talk about that, like sort of more or less through examples. By, you know, we'll talk about some examples, and here we start off with 4 different examples. 1, 2, 3, 4. 4 different examples of the ratio test in action. And I think these will give us a sense of when we might want to use the ratio test. So let's talk through this first example, and then let's talk about what made this example such a good example. Actually, let's talk through number 1 and number 2, and we'll talk about what made them such good examples for the ratio test. And I think, Deanna, that will go a long way towards answering your question. So this first one, we want to use the ratio test because at the moment we're told to use the ratio test. And the ratio test says that I want to set up, I'll sort of write this in the upper right, I want to set up an expression of the form a sub n plus 1 divided by a sub n. And so typically what I like to do is I just like to start with my a sub n. That's going to be exactly the expression that's written here, right? That's our a sub n. So I know in using my ratio test that the denominator of my ratio test is going to be just that whole expression, 5 to the n divided by n to the 5th. Now for the numerator, right, the numerator is going to be a sub n plus 1. And so that means that we're going to take the exact same expression as we had before, so this expression here, except every time that there was an n, we have to introduce an n plus 1. So this was the nth term, this was a sub n, and when I go to a sub n plus 1, all of those n's get replaced with an n plus 1. So to make that, you know, super duper explicit, this down here, this was our a sub n, and now up here, we're going to want to write our a sub n plus 1, and that would be 5 to the, not n anymore, but now it's n plus 1, divided by, this would become not an n to the 5th, but it would specifically become an n plus 1 to the 5th. Right, and that would be a sub n plus 1 because we've replaced all of our n's with an n plus 1. So according to the ratio test, we want to take that quantity, we want to take absolute values of that quantity, and then we want to take the limit as n goes to infinity of that to see what limit we might get. And what we'll see is actually that even though this looks complicated at the moment, because it's a sort of a fraction divided by another fraction, when we simplify everything, things will cancel really nicely. And this is really a hallmark of the ratio test. Oftentimes, we will apply the ratio test when we have a fraction for our a sub n, and the fraction involves terms that will cancel nicely once we set up our fraction divided by a fraction and we do the algebra to simplify it. So let me demonstrate. So limit as n goes to infinity. We have the same setup, but I want to point out that I can break this up into the 5 divided by, 5 to the n. I can break it up into those pieces, and I can break it up into these pieces, and I can consider them sort of separately. So if I wanted to, actually, let me do this over several steps, just because this is the first example of this. If I wanted to, I could rewrite this entire thing without thinking too hard about it by noting that the 5 to the n plus 1, that should be in a numerator. This is divided by n plus 1 to the 5th, so that should end up in our final denominator. And then down here, I've got the 5 to the n. That is in our denominator, right? That's in the numerator of our denominator. So that should really stay in the denominator of our final fraction. And then the weird one, the denominator of our denominator, the n to the 5th, that would come up here to our numerator. And what I'm just going to do is I'm going to write this exact same thing, but I'm going to group the 5 to the n pieces, right? So I have a 5 to the n plus 1 over 5 to the n. And I'm going to group my n to the 5th divided by my n plus 1 to the 5th. Right, so I'm just sort of cleverly grouping those. Now, in practice, I will usually jump directly from this step here all the way over to this step over here. Because I'll sort of know ahead of time that what I really want to do is sort of group my similar terms together. And the reason why I want to do that is because grouping similar terms actually lets me do some really fancy cancellation. On the one hand, I have my 5 to the n plus 1 divided by 5 to the n, and that is just going to equal 5. Right? Because 5 to the n plus 1 is just 5 to the n times 5. So in fact, this entire first term, put little parentheses around that, all of that is just going to become, that's like 5 to the n times 5 divided by 5 to the n, and those 5 to the n's are going to cancel out, so we're just left with a 5. At the same time, this second limit, or the second set of terms, the n to the 5th divided by n plus 1 to the 5th, that's not going to cancel, right? Nothing in there is going to cancel nicely. But I can recognize that as n goes to infinity, in the limit, this will just become the number 1. This becomes 1. In other words, the limit as n goes to infinity of n to the 5th divided by n plus 1 to the 5th is just equal to 1. And the reason for that, right, there's a few different ways we can see this. Way number 1, we can recognize that these are both polynomial terms, polynomial divided by polynomial. They have the same exponent, right? So their highest order term is an n to the 5th and an n to the 5th. And so we can look at the coefficients out front, and this is just a 1 n to the 5th, and this down here is also a 1 n to the 5th. So this whole thing converges to 1 over 1. If we're not comfortable with that sort of high-level analysis, we can also apply L'Hopital's rule. So as n goes to infinity, n to the fifth divided by n plus 1 to the fifth looks like an infinity over infinity. And after we apply L'Hopital's rule, and secretly in this case we would have to apply it 5 times, each of these polynomials will get whittled down to end up becoming a 5 factorial over 5 factorial. Whoops, apologies. Yeah, so each of these would become whittled down over several iterations of L'Hopital's rule, but in the end we would still see that the limit is equal to 1. So overall, what we get here is that by breaking this up into its 2 pieces, we have one piece corresponding to the original exponential 5 to the n, and another piece corresponding to the original polynomial n to the fifth. And we see that in each of those pieces, we can either simplify it, as in this case, or we can do some analysis to see what the limit becomes, as in this case. And so what we get overall then is that this entire thing becomes the limit as n goes to infinity. I'll keep the absolute value signs up there for a little bit. But this just becomes a 5 times a 1. And so the limit of the entire thing is just going to be equal to 5. Right? At this point, we would conclude that this limit is going towards a value L. That value L, in this case 5, is greater than 1. And we would say, so by the ratio test, the series diverges. Okay, and that's sort of full stop. I would call that the end of this problem. So again, right, the sort of flow of a typical ratio test problem is to set up this, this ratio. Oftentimes you'll end up with some weird expression that might involve like some fractions or what have you. So you'll want to break it up into its component terms. In this case, there was one term, right after simplification, there was one term corresponding to the exponential expression and one term corresponding to the polynomial expression. And each of those could get simplified further and sort of independent of each other. So that could be simplified in this limit either through algebra or through evaluating the limit. And that, like I said, is really sort of the hallmark of what makes a good ratio test problem, is if your original expression has these discrete pieces, like an exponential and a polynomial, that will be nicely broken up through algebra and will yield nice results. So polynomials will do this, exponentials will do this. It turns out factorials will do this too, and that brings us to our second problem here. So problem 2 says, let's consider the integral, the series as n goes from 1 to infinity of -1 to the n times n factorial divided by 100 to the n. And as a reminder, n factorial, right, is just 1 times 2 times 3 times ... all the way up to times n. So n factorial is just the first n numbers multiplied together, the first n counting numbers multiplied together. Whoops, I seem to have accidentally slid my slide over. Let's get back up there. Sorry, that's a constant annoyance here. Okay, great, we're back. So let's see. So in this problem, again, we're going to use the ratio test, but before I even begin the ratio test, let me highlight that I think the ratio test is a good choice in this case. I think it's a good choice because I have a fraction here. One of the terms is a factorial, which I've sort of hinted at is usually good with the ratio test, and the other is an exponential, 100 to the n, which is also good for the ratio test. So we have a fraction of individual terms that are often behave well with the ratio test. I have this -1 to the n, so this is an alternating series. But as we'll see, these absolute value signs that we'll throw up there mean that the alternatingness of the alternating series is unimportant. It won't actually affect things. So yeah, let's give this a go. What we have to do is we have to set up a limit as n goes to infinity. We'll have these absolute value signs, and we need the nth term in the denominator. So that's a -1 to the n. That's an n factorial. And that is a 100 raised to the n. Right? And then that's going to be over the n plus 1th term. So that's going to be -1 to the n plus 1 times n plus 1 factorial divided by 100 to the n plus 1. Okay, and so that's my setup. I need to simplify what's inside these absolute value signs. I have to simplify all of that, and then I need to take a limit as n goes to infinity. So let's do sort of two moves at once. Let's simplify and rearrange, and this time only, I'll deal with the negative ones. Afterwards, we'll just remember that the absolute value with the alternating series gets rid of these negative ones. But this time, let me actually deal with that. So as I break this up, I'll break it up into 3 pieces. Right? I have a -1 to the n plus 1 over -1 to the n times, I have my factorial piece, so that's an n plus 1 factorial divided by an n factorial times, and now for this one, I'm going to have a 100 to the n divided by a 100 to the n plus 1. Right? And just to make sure we're all crystal clear on that, notice the n plus 1 term fell into the denominator here. The n was in the numerator. And the reason for that, right, is because when I do my algebraic manipulation, my simplification, my 100 to the n plus 1 was in the denominator up here. So that has to fall into this denominator. My 100 to the n, that was in the denominator of the denominator. So that should fall, up here into the numerator. So notice my n plus 1 terms are in the numerator here, denominator here. So we just have to be careful that we get everything lined up correctly if we are simplifying and rewriting at the same time. Okay, now notice, let's take each of these in turn. For this first term, right, I promised the negative ones would cancel out, and they do. The absolute value of -1 to the n plus 1 over absolute value of -1 to the n, sorry, yeesh, -1 to the n, right? That's just going to be equal to -1, so that's the absolute value of -1, so that's just equal to 1. And in truth, that -1, the entire expression in these absolute value signs just ends up becoming a 1. Next up, we have got the n plus 1 factorial divided by the n factorial. And this is great. This is where we see that these factorials behave really, really nicely in terms of the ratio test. We have n, so let's keep in mind what the factorial is, right? So n plus 1 factorial, that's 1 times 2 times 3 times 4 times ... all the way up to n plus 1, right? So I'm going to write times n plus 1. At the same time, the n factorial in the denominator is just 1 times 2 times 3 times 4 times ... all the way up to times n. So it's the sum of the first n numbers multiplied to, it's the product of the first n numbers, and up here the product of the first n plus 1 numbers. And what we realize is that as we go forward, all of these terms, most of these terms, will cancel. So of course the 1s cancel, the 2s cancel, the 3s cancel, the 4s cancel, and so on. Everything in the ... cancels up to the n canceling. And so what we end up with is just whatever's left, and that is an n plus 1 in the numerator. So we do some analysis and we see that there is an n plus 1 left over in the numerator. And so the factorial actually simplifies really nicely as well. Finally, we have this exponential term, right? And what we'll see in the exponential term is that we end up with 100 to the n divided by 100 to the n plus 1, as we said last time, is just 100 to the n times 100. Right? And so we end up with a 1 over 100 here. Notice the similarities between this problem down here and this problem right here. Right? So these exponential expressions behave very similarly. With a 5 to the n, the ratio test left us with a 5. With a 100 to the n, the ratio test leaves us with a 100. In this case, the 100 is in the denominator, because the exponential term was in the denominator. So we end up with this expression of 1 over 100. And what that means is, in the end, this becomes the limit as n goes to infinity of n plus 1 divided by 100. And we see that as n goes to infinity, even though we're dividing by 100, our numerator will get bigger and bigger and bigger and bigger. And so this actually goes to infinity, right? This limit is equal to infinity, or this diverges to infinity. And in particular, it's definitely bigger than 1. So what we can conclude is that this series also diverges. Okay, so both of these series on this first set of problems ultimately diverge. We see that because the limits we end up computing are larger than 1, right? This limit went to infinity, the previous limit went to 5. But we also see several examples of what are really good problems for the ratio test. They typically involve some fractions, right? So they're expressions in which the a sub n become fractions. And the individual pieces of those fractions, like the numerator and the denominator, are expressions that simplify well under the ratio test. So things like factorials, exponentials, and polynomials all simplify super well under this ratio that we set up. So Dan, I hope that also sort of hints a little bit at when we might use the ratio test here. Okay, any question about these first two problems? I think we'll probably skip problems 3 and 4 unless there's a strong demand if people want to go through them. I'll skip those for the moment and we'll move on to look at some future problems. 3 and 4 can be exercises for you to do on your own. But any questions about these first two?
Real quick, could you re-explain your thinking with the factorials?
Yes, absolutely. So sort of focusing on this part right here, you mean? So
Yes.
happy to, absolutely. So a nice thing about, I mean, so first of all, the definition of a factorial, right, is that once I have an like something factorial, it becomes 1 times 2 times 3 times ... up to that counting number itself. So, n, I'm assuming, is a counting number. It's, I'm not plugging in pi, I'm not plugging in -1, but I'm plugging in like 5 or 50 or some counting number n. So what that means then is that n plus, that at n factorial is all of my numbers 1 times 2 times 3 times 4 up to n, while n plus 1 factorial is 1 times 2 times 3 times 4 all the way up to n plus 1. And so what I've done in my writing is I've hidden most of those numbers in the ... but I'm sort of acknowledging that I end here at n, and that in this numerator I end at n plus 1, which means that the previous term must have itself been an n. So I'm just sort of including that outside of the ... But I'm doing that to highlight that when I set up this fraction, right, in a fraction, if I have a common multiple in the numerator and denominator, I can just cancel them right out. And so with factorials, you end up getting lots and lots and lots of common factors in the numerator and denominator. So this 2 that was here cancels out with this 2 that was down here. This 3 cancels out with this 3. This 4 cancels out with this 4, and so on. And so all of these terms end up canceling, including the n that was up here cancels with that largest term, that n that was down here. So the only thing that's left over is this n plus 1 in the numerator, which is why n plus 1 factorial divided by n factorial is actually equal to just n plus 1. So sometimes I think there's something that can be lost or a little confusing when we use the n, like the n expression. So maybe to go through one explicit example, which I'll put here in the middle in this gray box. If I wanted to look at, let's just say 5 factorial divided by 4, let's say 6 factorial divided by 5 factorial. Right, if I wanted to look at something like this, this becomes, you know, the numerator is just 1 times 2 times 3 times 4 times 5 times 6. The denominator is 1 times 2 times 3 times 4 times 5. And now if I'm not thinking about this cleverly, I could multiply the entire numerator out. So that entire numerator is 720. I could multiply the entire denominator out, so the entire denominator is 120. And then I could, you know, do that division. That's if I don't want to be clever about it. If I want to be clever about it, and I love to be clever about these things, if I want to be clever about it, I can cancel out the 1 and the 1, the 2 and the 2, the 3 and the 3, the 4 and the 4, and the 5 and the 5, and the only thing that's left over is a 6 and then this placeholder 1 in the denominator. And so we realize that actually this entire thing does equal 6, which I could have done by doing 720 divided by 120, or I can see it with this really clever sort of collective cancellation here. And when I'm dealing with the abstract n, that's really what I want to do, is do this abstract cancellation. So in this case, the numerator was n plus 1 factorial, the denominator was n factorial. The only thing that's left over is n plus 1. Yeah, thank you for asking. Happy to talk more about that. And we'll see in the future that if I have more complicated expressions like 2n factorial, it's possible that something more complicated will happen. So we'll see that going forward, that we want to be cognizant of how we set this up and how we are canceling these terms and seeing what's left over. So love it. Thank you for the question. Any other questions on these first few? Okay, great. Well, if that is okay, I'm going to clear these. Let's move on to something new. Okay, so I said for the moment that we will skip these problems. Let's go on to problem 2 to see what happens here. So problem 2 is another example of how we can use the ratio test well. The ratio test, maybe I should say, here's a series, sum as n goes from 1 to infinity of b sub n, but the b sub n's are not explicitly defined. Instead, they are defined using this recursive element where I define each term, b sub n plus 1, in terms of the previous b sub n. Right? So this is often called a recursive sequence or a recursive definition. We call it a recursive definition if you define the first one, so that's b sub 1, and then you define each successive one in terms of the previous one. So if I had wanted to, I could calculate b sub 2, right? B sub 2 is going to equal 1 plus a half times b sub 1, right? Well, that's just equal to 3 halves times, well, b sub 1 was 1. And so that's ultimately equal to 3 halves. So b sub 2 in this case is 3 halves. B sub 3 is going to be 1 plus, ooh, no, I made a mistake, didn't I? This should have been 1 plus a half raised to the second power. So that should have been 1 plus a half squared. That should have been 3 halves squared. And so that should have been not 3 halves, but that actually should have been 9/4. Okay, and this is already going to get kind of messy, we can see. So b sub 3 is 1 plus a third cubed times b sub 2. So that's going to be 4/3 cubed times 9/4. And already I don't want to deal with this, right? Like this is going to be some ugly fraction. And we continue to proceed, right? So we calculate b sub 4 by plugging in 1 plus 1/4 to the 4th times b sub 3, and so on and so on. So each successive term in a recursively defined sequence, each term is defined in terms of the terms that came before it. But as a result, we often end up with these complicated expressions where there's not a clear pattern what b sub n should be. In other words, there's not an explicit way to write b sub n just as a function of n without referring to the previous term. So that makes it hard to write down a nice formula for b sub n. That makes it hard to explicitly write down what this series should look like. And that makes it hard to use just about any series test that we have, except for the test for the ratio test, except for the ratio test. Because notice, if I wanted to set up my ratio test here, right, that would involve me taking a limit as n goes to infinity of the denominator is b sub n, the numerator is b sub n plus 1. And when it comes to successive terms here, I have a nice way to write b sub n plus 1 in terms of its previous term, b sub n. So in fact, the recursive definition is not a drawback when I use this ratio test, because the b sub n plus 1 can just be written in terms of b sub n. Specifically, it's 1 plus 1 over n to the n, 1 plus 1 over n to the n times b sub n. Right, so I'm using that recursive definition here to nicely rewrite my b sub n plus 1 into something involving b sub n. And that's great, because at this point, we can get that the b sub n's just nicely cancel out. Right, so again, the recursive definition is often a really challenging one to work with. But in the case where I'm dealing with a series and I'm looking at the ratio test, the recursive definition is not really a drawback. This just becomes now the limit as n goes to infinity of 1 plus 1 over n to the n. And that's one of our really challenging statements. That's one of our really challenging examples, I should say. This is one of our Calc1 examples that we know and love. This was one that we could use L'Hopital's rule to apply, I think I said that poorly. This is a problem that we can now use L'Hopital's rule to deal with. This is of the form, this is of the form 1 to the infinity. And so we would apply L'Hopital's rule. We'd have so much fun doing that. Well, how much fun that was. And what we would ultimately see is, in the end, this would end up equaling lots and lots and lots of L'Hopital work. This would end up equaling E, surprisingly enough. So that limit is equal to E. E, I don't remember many facts about the actual number E, but I remember that it's 2 point something. Sort of like how pi is 3 point something, E is 2 point something, and in particular, E is bigger than 1. And so we can say, since our limit, E, is bigger than 1, by the ratio test, this series diverges. And then we are good to go. Now, I think I saw a hand raised at some point. My screen was partially blocked, so I didn't completely see it, and I didn't see who was raising their hand. But yeah, if anybody has a question, let me absolutely pause here. Please let me know.
I was wondering where you got the denominator, or if that's just part of the recursive like sequence.
Ah, gotcha. Thanks. So the question, Jose, as I'm understanding it, is where did I get this denominator right here? Is that right?
Yeah.
Okay.
Yeah.
Yeah. So that is not part of the recursive definition. That is actually, if you let me scroll back 2 slides and ignore the awfulness of the superposition of the writing and the slide. This is actually from the definition of the ratio test. So the ratio test asked us to take the n plus 1th term divided by the nth term. And that was sort of how we set this up in this, oh no, wait. This is how we set up our previous work in each of these. And it just so happens that in this case, when I set up the n plus 1th term and the nth term, the n plus 1th term can be written in terms of the nth term, so we get that nice cancellation. But that's an artifact of the ratio test itself, not anything special about this problem.
Okay. Yeah, I was just confused. I didn't know we were doing the ratio test. I was just like, wait.
Yeah, sorry.
Okay.
So yeah, I would say, so a takeaway message from this page, right? Again, we're trying to document not only how to do these tests, but when it is worthwhile to do these tests. So oftentimes, I don't know why I said oftentimes, it takes forever to write out on this tablet. Oftentimes a recursive series, or a series that's defined recursively, will be a good candidate for the ratio test. Right, and that's exactly because oftentimes this recursive element leads to this kind of nice cancellation. Okay, I love it. Great question. Any other questions while we're on this slide? Okay, cool. Let me go ahead and clear this writing and let's see what else we've got. So let's see an example of the root test. Oh, look at this. I'm so sorry. I make these slides just based out of the previous, like, I guess I make these slides out of the activity sheet. It looks like I forgot to make some separation before problem 3 and problem 4 here. So this is problem 3, determine whether or not that converges. This is problem 4 right here. So let's jump to problem 3. I'm rereading problem 4 right now, and that might not be, yeah, I'm rereading problem 4 right now. It seems a little odd. Let's take a look at problem 3 though, absolutely, because I want to, yeah. We'll take a look at problem 3 because this is our first example of the root test that we've actually talked about out loud. So the root test, right? As a reminder, the root test asked us to take a limit as n goes to infinity of the nth root of the absolute value of a sub n. So the nth root, that's like taking a 1 over n expression, or that's like taking a 1 over n of the absolute value of the nth root. I'm sorry, the absolute value of the nth term. So that should be a sub n in here. And a sub n in this case is just going to be this entire expression up here. So a sub n can be rewritten, throw those absolute value signs back up there. A sub n can be written as n divided by 2n plus 3 raised to the nth power. Okay, now it turns out there's going to be some really nice cancellation that happens here as well, which is really indicative of when we would want to use the root test. So again, going back to thinking through when do we want to use a certain test versus another test, in this example, the big hint that we want to use the root test is that our term a sub n, right, this term right here, a sub n, is sort of, it's some big expression, but then it's all raised to the nth power. That is our big clue, right? So the reason we want to use the root test in many ways is coming from this expression right here, that n as an exponent. And we see why. It turns out, or we can notice, that these absolute value signs are not doing a whole lot here. This expression will always be positive no matter what. Specifically, you know, in this example, n divided by 2n plus 3 raised to the nth power, that will always be positive. And so the absolute value signs can be ignored, right? They don't affect anything. And so what we end up with is this limit we have the whole expression n divided by 2n plus 3. That's raised to the nth. And then that is raised to the 1 over n, right? So we're taking the nth root of that thing. And the reason why this is so great is because the n and the 1 over n, by rules of exponents, just cancel each other right out, right? We know that a raised to the b raised to the c by rules of exponents is just equal to a raised to the b times c. And so here this becomes the expression in the innermost parentheses, that n to the 2n plus 3 raised to the n times 1 over n. And so those cancel each other out, and, or maybe rather they multiply together to get a 1. And so this really now becomes the limit as n goes to infinity of n over 2n plus 3 raised to the 1 power. So that just becomes limit as n goes to infinity of n over 2n plus 3. And by examining, by comparing coefficients or by using L'Hopital's rule, right, this just ends up becoming 1/2. And so this is a limit that is less than 1, right? And we can conclude, since the limit is less than 1, we conclude that this series converges absolutely. Awesome. Full stop. Full stop. Let me pause for a moment for that one. Again, I sort of split this up into problem 3, which is here, and problem 4, which is down there. Any questions about problem 3? We can talk about problem 4 in just a moment. Okay, so problem 4 is kind of interesting. Use the comparison test to show that this series here converges. So I'm going to erase my work from problem 3. Use the comparison test to show that this series right here converges. Okay, so this is a weird one, weirder than the ones that we've seen so far. It has a strange looking fraction, and it specifically says use the comparison test to show that this converges. So as a reminder, the comparison test, hang on, let me pull up my pen here. Right, so we're trying to use the comparison test, and we're trying to show that this thing converges. So as a reminder, the comparison test, I'll sort of draw it in this little blue box over here. The comparison test suggested that we ultimately wanted to compare a series of a sub n and compare it to a series involving b sub n. And if we knew that the individual terms, right, so if we knew that a sub n was always positive or always non-negative, and if a sub n was always less than or equal to b sub n, then as far as series would go, the sum of all the a sub n's would be less than or equal to the sum of all the b sub n's. So we could conclude that this inequality held true if this inequality held true. And that allowed us to conclude that if the sum of b sub n converges, then the sum of a sub n converges. And look at that, I made my box way too big. But yes, so we also could draw the conclusion, I should put it up here for completeness, we could draw the conclusion that if a sub n diverged, then b sub n also diverges. Right, so we could draw both of these, or I should say either of these conclusions. A more appropriate blue box. Okay, so here we're trying to use the comparison test and we're trying to draw a comparison test conclusion about convergence, which means that I really want to focus on this first bullet point. What that means as far as strategy goes is that I want to really think about this series. I want to think about this series as a series a sub n. And I want to find a better is a bad word, I want to find a different series, b sub n, that is bigger than a sub n. Right, so if I'm trying to draw this conclusion, my goal is to conclude that this series converges, so that should be my a sub n. I want to find a bigger series, b sub n, that sits above it, or is larger than it. So I want to find a series that is bigger than this, but that I can definitively show converges, and then I'll be able to draw this conclusion. So that's a little tricky. That's going to require a little bit of guess and check, or a little bit of clever thought here. Because we are really in the world now where I'm looking at the ratio and root test, I'm going to be thinking in terms of ratios and roots, and can I apply either of those tests to a similar sequence? And I'm going to notice that n to the n term, which is a little goofy, right? N to the n is not wonderful, but we've just been talking about how n's in our exponents can potentially lead to expressions involving the root test and how the root test can be helpful in those situations. Specifically, here I had a thing involving n raised to the nth power. Here I have a thing involving n raised to the nth power. So an idea, right? And again, this is all kind of educated guess and check, so there's not a clear-cut immediate answer, but an idea is to look at not 1 over n to the n plus 3n, but let's look at 1 over n to the n by itself. This is an expression that maybe we can hope to use the root test for, and it's an expression that we can maybe hope to compare to this expression here, right? So maybe this is a good expression for b sub n. Let's find out, right? So what we're really hoping for is to find a b sub n that is both bigger than a sub n and that itself converges. Let's take a look. Let's find out. So if we're looking at n to the n, I can try to compare my a sub n, that's this, and I can compare that to 1 over n to the n. And the question is, which one is bigger, right? Which one is bigger? And so we've done this kind of analysis before when we were looking at the comparison test. We can recognize that because this term, actually, let me circle the other one. Because this term has a larger denominator, right? There's more stuff, more positive stuff happening in this denominator, so this denominator is larger. That will make the entire fraction smaller. So we actually get this direction for an inequality, right? Larger denominator on the left means a smaller fraction on the left, and so we get this inequality, which is great. That's exactly what we wanted to show here, right? So we end up getting that that inequality is true, and so we can conclude that the sum of 1 over n to the n plus 3n is actually less than or equal to the sum of 1 over n to the n. Awesome. So we're well on our way towards setting up a comparison. We've got the correct inequality that we want. Now, big question, does b sub n converge? So does this series converge? Because if it converges, then we will know this smaller series necessarily converges as well. Let's give it a try. So, because we have an n to the n, right, an expression involving n raised to an exponent of n, I think this could be a good candidate for the root test. So let's use the root test on 1 over n to the n. And what that means is we will need to take a limit as n goes to infinity of expressions of the form, right? It'll be an absolute value of 1 over n to the n raised to the 1 over n power on the outside, right? And that's because we're taking the nth root here. So that's a 1 over n. Okay, now, just like before, the absolute value signs won't actually matter in this case because everything inside the absolute value signs is positive. And so this becomes the limit as n goes to infinity of 1 over n to the n raised to the 1 over n power. And by rules of exponents, this is a great day to review some rules of exponents, right? If I have a over b raised to the c power, that's just equal to a to the c over b to the c, right? We can make that its own little side scratchwork box. So we have an a to the c over b to the c, and the result then is going to be that this becomes the limit as n goes to infinity. This becomes a 1 over 1 to the n, 1 raised to a 1 to the n over an n raised to the n raised to the 1 over n. And just like before, those will cancel. So this whole thing simplifies down to the limit as n goes to infinity of 1 over n, and that is definitely 0. So what we can conclude, right, we can conclude, I'm going to try this. We conclude by the root test that the series, maybe this is more awkward than it's worth, we conclude by the root test that the sum of 1 over n to the n converges. Therefore, by the comparison test, we know that our original series, the sum of 1 over n to the n plus 3n, also converges. Full stop on problem 4. Okay, another time for a good pause. This was, I think, the most challenging one that we've done yet. It involved both a comparison test and a root test. So there was a lot of sort of creativity that was necessary here, and a lot of places to potentially get lost. So any questions at the moment? All right, cool. You all have been such a good audience this morning. All right, let's turn our attention then to one of the next few problems.
Oh, Dr. Ross, I have a
Oh,
question.
yes, I'm sorry. Yeah, Chris, go right ahead.
Is the constant in the numerator always going to be 1, or can that change? Like when we use the like when we set up our comparison, we had 1 over n to the n. Is like, could that ever be like a different coefficient in the numerator?
Yeah, absolutely. Thanks for asking that question. It absolutely could be a different coefficient. Let's think here. Well, an easy way that it could be, I'm going to pull out the color very bright green to highlight this. So I think, for example, if we had been asked to show that this converged, right, sort of 3 over blah, 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 all of that, I could have then immediately compared that to 3 over n to the n. We would have gotten the correct comparisons all the way down. And in the end, we would have had to take this limit, this limit, this limit. And in the end, 3 over n would have gone to 0 just as easily as 1 over n went to 0. There wouldn't have been a major difference there. I think there are more complicated examples that we can also cook up, in which it's not just changing a single constant, but if I changed like this expression, I'd have to think a little bit about this. Okay, not to make it too complicated, but if I were to change this instead to, I'm worried I'm making it too complicated. If I were to change this instead to, let's say something like arctan of n. Ooh, that's possibly complicated. Arctan of n. Well, off on the side, I could remember that the arctangent, or the inverse tangent function, has this horizontal asymptote. As it gets bigger and bigger and bigger, the arctangent function never gets bigger than pi over 2, right? The arctangent function off on the side here kind of goes up, and then goes off and never gets bigger than pi over 2. That's as big as the inverse tangent function ever gets. And it never gets to that height. So I could compare arctan of n over n to the n plus 3n. I could actually compare that to pi over 2 over n to the n, right? And I would end up with the correct comparison, which is that the a sub n, right, here's arctan of n, that would be less than or equal to pi over 2 divided by n to the n. The reason there being that the numerator is always smaller than this numerator, while at the same time, this denominator is always bigger than this denominator. So overall, this fraction will be smaller. It has a larger denominator and a smaller numerator than this one here. And so I could ultimately go through drawing the same conclusions along the way about pi over 2, pi over 2, pi over 2, and I'd end up getting over here the expression, I guess this would become a pi over 2 raised to the 1 over n, which we have to think a little bit about that. And I think I should have done the same thing when it was previously 3 over 1 to the n. I did go a little too fast there. But this limit will actually also equal 1. As n goes to infinity, taking bigger and bigger and bigger nth roots of pi over 2 ultimately gets me closer and closer and closer to 1. So this would end up being a 1 divided by n, which would still go to 0. So yes, Chris, we can have things other than 1 in that numerator. It would make this part a little bit more confusing, and maybe that's what you were talking about. Maybe that was like where your question was sort of anchored around what happens here, and maybe I misinterpreted that. But yeah, it turns out that if I had some other constant number there, the constant raised to the 1 over n would get closer and closer to 1 as n goes to infinity. And so in the end, that limit wouldn't really make a big difference here. Let me pause and ask, does that answer your question? And was that really sort of the part you were focusing on?
Yeah, it answered it. I was just like, I just wanted to know if there could be a different one because I think like on the homework, like I just kept putting like 1 over, like whatever like something that could work in the denominator, but like I just wouldn't get the right answer. So I assumed that you could, but I didn't know like what you do to like find out what to put in the numerator.
Gotcha. Yeah. I think in general, for something like the comparison test, it really is a case-by-case situation that depends on looking at the expression and trying to figure out what is the best thing to compare it to. And the only reason that we ended up comparing it to a 1 in our original pass on this problem was because it started with a 1 up here. If there was something else in the numerator, as you've sort of seen, we would have had to compare it to something else.
Got it. Thank you.
Cool. Yeah, no problem. Thank you. Great question. Any other questions while we're sitting here? Okay, so I'm looking at the time now. We've got about 7 minutes, a little more than 5 minutes left. Let me quickly, I'm going to scan through the rest of the problems. There were a few other problems that I think are very, very worthwhile. These problems here are really worth going through if we're dealing, because these get a little more abstract in the sense that we are dealing with a arbitrary but constant value of capital M, right? And I think those are absolutely worth going through. Notice these problems will be very similar to the first few problems we looked at, right? This is like an exponential term divided by a polynomial term. This is an exponential term divided by a factorial. And in that sense, they really look like those first few problems that we had here. Right, and so I would encourage you to go through those, leaving your M arbitrary and sort of just as a constant M, and seeing what you get in your final ratio, right? Your ratio will still have an M in it, but it's a constant M, and so it's possible as you take your limit that you end up getting a reasonable answer that you can analyze depending on what M is. So I'd encourage you to work through problems 5 and 6. The final problem was a challenge problem, which you're invited to work through or not as you are interested. So I actually want to pause a little bit early here. We're about 5 minutes early, and I just wanted to mention briefly the first quiz, which was taken on Friday, which was due Friday. And so, right, that was this past Friday. I think most of you were able to successfully take the quiz, which I was thrilled about. A couple of you had minor technical difficulties, but I reached out to you individually and have gotten responses from most of you. So I think everything there is going reasonably smoothly, at least on my end, from what I can interpret. If you had issues in taking the quiz that you want to bring up, or ways in which you think it could be streamlined, could be easier, I'm of course open to those, right? This is sort of a new medium for taking quizzes and for handing them back. So I welcome any feedback that you have. All of the quizzes that were handed in to me have now been graded and handed back to you. And I just wanted to highlight, because it's unclear on my end exactly what you see when you take a quiz, or when I grade something and give you feedback, it's not clear to me what gets signaled to you. So every single quiz had a grade of either 0 or 1, and I basically graded them all as a 1 to signify that they were graded. However, right, these are mastery-based quizzes. You got a grade of either mastered, progressing, or requires reassessment, just like we've seen in the class so far. And in order to actually see what grade you got as far as mastered, progressing, or requires reassessment, I think you have to go into the quiz itself to see my feedback. Right, so every single quiz, I marked it up using, sort of the Moodle grading system. So I wrote on the quiz, and I included in the comments section what your actual grade was for that quiz, whether it was an M, a P, or an R. So just in case you weren't clear on that, I would encourage you to go into Moodle and to check each and every one of those quizzes for the comments to see what your grade on that was. At this point, the grading for reassessments and for progressing quizzes is the same as it would have been in the semester. So if you got a grade of progressing, that means you made some small mistakes. Send me an email with those corrections, and I'll bump your grade up to mastered once I verified that your corrections are correct. So nice, quick, easy way to take care of that. Grade of requires reassessment means that you will have to take a reassessment quiz, right? Just like during the semester, it's not the end of the world, but I encourage you to do it sooner rather than later so that they don't begin to pile up. To take a reassessment quiz, send me an email saying that you want to take the reassessment quiz. I will send you an email with the quiz, and then just when you are ready, open that PDF, take the quiz, take a picture of it, save it as a PDF, email it back to me, right? So these reassessment quizzes will be done on your own time and we'll coordinate through email. But just go ahead and send me that email as you start to feel more prepared to take the quiz. Give me, as always, I'll respond to it as quickly as I can, as soon as I see it, definitely within 24 hours. I think that's most of what I wanted to say as far as the quizzes go. There was one quiz question that I think everybody struggled with a little bit. That was the quiz question involving the integral test and trying to determine which range your series might be within. So your series converged, but what range of values might it converge to, or might it converge to between? I said that terribly. Your series converged to some number L. It was a multiple choice question in which you were trying to figure out which, where your number L might lie, between what range of values. I think that was universally a challenging question. And so I actually recorded a video yesterday and I uploaded it to YouTube, just sort of talking through that problem. So if that was the one that you struggled with, or if that was one that you struggled with, there's a video on YouTube in our classwork section. I think it's like a 15-minute video in which I just sort of talk through my thought process for the problem. So I would encourage you to check that out and to let me know if you have any questions. Love it. So that really just about brings us to time. I'll stick around for a moment if anybody has any questions, but I'm going to stop the recording now, and I hope you all have an absolutely wonderful rest of your day. Have a great Monday. I will see you all either in office hours or by email, or I will see you on Wednesday.